Welcome to Beyond the Qubit. I'm your host, Frank Dekker, and today I have Evert van Nieuwenburg as a guest on the show. And Evert, he's all about gamification of quantum computers, and he works at the intersection between AI and quantum computing. In the past, Evert has done a lot of experimental work on quantum phases. Yeah, but now in his daily job, he's associate professor in Leiden. Evert, thank you. I'm excited. Thank you for being here.
Thank you for having me.
Do you want to become the DeepMind of quantum, Evert?
What? Why not? DeepMind is a company that started and they just said, we are going to solve the problem of intelligence, right? And they said, being able to play a game somehow must mean, or it has to do something with being intelligent, right? You have to be able to plan and predict your opponent and have logic. Claude Shannon, one of the fathers of computer science, and also Ada Lovelace, going much further back, they both said essentially the same thing. They said, now we have we have computers, and maybe at some day, almost not imaginable, computers can even play games, right? They thought about chess. So having this focus on, let's say, I want to not crack intelligence, but I want to crack quantum intelligence or quantum computing. And then instead of saying, I'm going to focus on a particular use case, just saying, what do we need to understand quantum, right? What is the thing that we need to really understand? What's the playground in which we can simulate it and work on it? And I think here, again, the answer is games, because they give you so much structure, right? They just, you have clear rules, things that are allowed and things that are not allowed. You have a clear winning condition and a loss condition. And so it puts so much more structure on your problem that I think it's worth doing the gamification of quantum problems.
Could you give a short introduction about yourself and what excited you about quantum and in the start of your career, quantum phases?
Yeah, this is a challenge for me to keep short because there's so much that comes to mind for me now. But I started out in theoretical physics, studied in Leiden, and then I moved to ETH in Switzerland, and then California, Caltech, and Denmark after that for 3 years. And somewhere during my PhD at the end, which was in physics, I saw this work or paper doing a very basic thing with machine learning and physics. And then I thought, I can do that. And so I implemented one of the first papers that did neural networks, which was for classifying phases of matter. We can talk more about that if you want later. With machine learning, an application of machine learning to physics. And that's the paper that we called it Learning by Confusion. That's the paper that I think kickstarted my career. It got me invited. And then from then on, it grew into machine learning for physics. And so more and more, I went into that direction, and more machine learning for quantum systems. I think that's a very short summary of my career with the highlight. Yeah.
What are the problems you mentioned before the interview? We had a call, an introduction call, and you mentioned that you were all about gamification of quantum. What do you mean with that, and what excites you?
Okay, so there are again many different angles which I think make sense from the gamification. And just to highlight this, from what comes out to me often is that when I look at or read texts of some of the famous physicists and computer scientists that I know, for example, Richard Feynman should be familiar probably to the physicists. He had this statement multiple times that he thinks you should be able to really just play with physics. You should have an intuitive understanding and just enjoy doing it, and then the ideas will follow. And he attributes his Nobel Prize to this. He stopped liking physics. At some point, he just went back to playing around with physics ideas, and he came across these diagrams that he made. And those are the Feynman diagrams we now all know, and it got him the Nobel Prize. And I think this way of doing research is now looked at as not serious, right? Usually playing or games is not for true or real scientists. I think that's a shame, because science ultimately in research is an out of the box, it is a creative endeavor. You have to come up with new ideas. And you see it in the jargon. We still use toy models in physics to understand simple problems. And so I'm trying to reinstate this idea that it's worth doing fun research just for the sake of doing the research. And you have to believe that at some point that will lead to new insights. And then there's evidence for that is all over the place. So this is the idea that, that's one of the gamification of the research. And there's a few more I can talk about, but I will mention one now, which is that, we have AIs that are incredibly good at playing games. This is what DeepMind gave us, right? They made agents that know how to play chess and Go. And now those same agents, they can use the same techniques to predict weather patterns or do folding of proteins. And so in a nutshell, if I can take my hard quantum problem, turn it into a game, which is not an easy task. This is non-trivial. You might be surprised how hard this is. But once I have it formulated as a game, I can go to those powerful AI methods that know how to play games and use them to solve that problem, right? And if the solution of winning that game is equivalent to solving my hard quantum problem, then I'm done, right? That's
one of the first use cases was also the media industry for special effects.
Yeah.
But for content creation, what resonates with me is that I think it's a different kind of mindset and different kind of discipline.
Yeah.
So the creatives might have a different mind,
absolutely,
and brain, and they are differently wired than quantum physicists.
Yeah. Yeah, I know.
So that could also bring benefits to
this is exactly the other point I wanted to make, because no one predicted when the first computers were being made that we would be using it to do this, right? Record a podcast or to keep track of your appointments, or this is the whole point. I think you would be hard-pressed to find a technology that we fully predicted, right? We knew exactly what it was going to do and that it didn't find any other creative use. And so, indeed, trying to tap into this mindset of the creative people and give them access to quantum content, quantum phenomena, quantum things, right? And again, games come in, right? Because how do you get someone with no quantum background to have some intuition of quantum processes? I think games are a good way of doing that. But then it just takes a few, or this one kid playing around with this, coming up with something that me or the experts would say, hey, I didn't know you could do that with quantum circuits, right? And then it will grow from there.
Evert, can we dive a little bit more into your gamification of quantum initiative?
Yeah.
What problems do you solve with that?
The most recent one, and the one that we're working on more and more now, is quantum error correction or quantum error decoding. That's one of the next frontiers for quantum computers, is to have them error corrected. We call them those fault tolerant quantum computers. And because you cannot measure and look at your quantum computer and the qubits, because measuring them will project them and then you lose all the quantum information, you have to find sort of indirect ways of inferring whether errors happened. And we do that with so-called quantum codes. And you should imagine something like, maybe I can give you a bit of an intuition for this. So those codes, they cannot tell you whether an error actually happened, but they look at, let's say, a group of 4 qubits, and then they tell you if there was an even or an odd number of errors on these qubits. So they tell you something about either it was 1 or 3 errors, or 0 or 2 errors, right? Or even 4. And so you get all that information of all these qubits, and for each group of 4, you get to know even or odd. And from that information, you have to infer what the most likely set of errors was. You can never do this perfectly by construction. You can only make an estimate of what is the most probable or most likely set of errors. And so now it's a game, because now I give you should imagine just a picture like a chessboard. And on that chessboard, on each square, you see a green dot or a red dot, and green is even amount of errors on the corners of that square, and red is the opposite. And so I typically don't show the green one, so I just give you a chessboard with a few red dots, right? And your task is you can move the red dots from one square to the next, and you have to merge them. I can tell you all about how, like, why this corresponds to doing error correction, but ultimately the game is that. Chessboard, red dots, and you have to find a path in which you merge them. This is a game. I mean, not a super fun game, if you will, if you play it as a human, but perfectly suited for an AI, right? It's like chess, but now you move red dots. And so merging those red dots is equivalent to removing the errors in your quantum computer, in your quantum code. And so if you find the right strategy for merging them, you also have a good strategy for doing quantum error decoding.
I want to switch topic a little bit on quantum machine learning use cases.
Yeah.
You did a lot of work on that. When you evaluate claimed use cases, what are the first two questions that you ask to test the credibility?
Excellent question. I ask, is this problem truly a hard problem for classical computers, right? It must be true that this is really a problem I could not have done with my classical computer, right? And then maybe not like right now, because like I said, I think almost all of these things I can do on my laptop right now. So it really has to be the structure of the problem. If I make the problem larger and larger, does it become harder and harder does it become harder faster for a classical computer than for the quantum case? It has to have that property. Otherwise, it will never be relevant. And I also ask, did they do this feasibility study? Did they actually run it on hardware? Did they take into account all of the issues that come with that? Because yes, Grover's algorithm gives you a quadratic speedup for doing an unstructured search. But you will find that if you actually try to do that on hardware, you also have a quadratic slowdown somewhere else in either the uploading or the readout, right? Yeah. So for real world data problems, it's going to be this is a critical thing to evaluate, right? Do you actually get the speed up if you take the whole thing into account? Which incidentally means if this is a claim for speed up or like a quantum machine learning case where the input is quantum, so you do that on the quantum simulation directly, I think then you're already in the green for this, because then you don't have to have this uploading and readout thing. But yeah, is it truly a hard problem? And did they realistically take into account all the other things that need to be covered? Those are the first two questions I have.
Okay, thank you. Which categories of use cases have quietly slowed down and which categories strengthened over time?
Yeah, so the things that come to mind for me are the variational quantum eigensolvers, which people at some point thought these are interesting things to use for quantum chemistry. It is a subset of quantum machine learning. Quantum machine learning is this fascinating thing where, like I said, for many real-world problems, it is not clear and it's tipping a little bit into the direction of really not sure how and where it's useful. But at the same time, we have so much evidence that says there has to be a thing where it is useful, right? We're looking for that. And so this is on one hand, going down, but also, more and more interesting because it's such a challenging problem. Logistics and optimization, to me at least, when I see use cases and from the sentiment I'm getting, is becoming that sort of quietly weakening, I would say. So this is because of those things I mentioned before, like, that for optimizing networks of 1,000 nodes, we have such good and fast classical algorithms. It's not clear if you get that speed up overall. So this sort of optimization logistics is less. This is my perception. I know some people will think differently. So that's one. What has strengthened and is clearly strengthening still is really the application to intrinsically quantum problems, like simulating molecules, making new materials, because ultimately they are quantum systems, right? So applying it to chemistry and physics problems for better solar panels, better energy, better batteries, they are gaining in traction.
And where do you base that evidence on?
So this, I mean, basing on it is papers, is like research, right? Is research, because that's the thing I know how to evaluate most easily, right? But also a little bit in terms of, I do keep track of companies and investments, right? And some companies I wonder, like, why is this a company? How does this exist, right? But I think the strongest evidence really ultimately is, it's fun if someone wants to say, I can do better logistics with quantum computers. But if at the same time we have a hard proof that it will not work, it will not scale, then I would trust the proof, right, in this case. There are cases, and I should say this out loud, where this is not true, because if classical computers only did the things we knew how to prove, we would not have had AI, right? I mean, AI works empirically, and there are many things we don't understand about them. So it's also a matter of taking this risk. But yes, papers. It's just use cases on the optimization and logistics. I don't see them really doing things that I'm convinced by you could not do with classical computers better, at least in the next 5-10 years. And given my background in condensed matter physics, before quantum computers were a thing, there were already simulators of materials that trapped ion people. They were doing this in cold atoms. They were doing this for a long time. They were simulating the Hamiltonians of quantum systems, trying to find how do superconductors become superconducting, right? And for some reason, people didn't think of them as quantum computers because you could not use them for generic computations, but they are already excellent at simulating specific quantum systems. And so those types of quantum computers are worth it to me. And they are, people are now realizing in the literature also that it makes sense to call those quantum computers, they're just specialized quantum computers.
Okay, fair enough. Can we talk a little bit about the implications for quantum computing and verification? As quantum computers scale, do you think machine learning-based diagnostic will become unavoidable?
For now, I think yes. Somehow I have trouble imagining in 30 years, let's say when we have in that scenario stable working quantum computers, I would somehow be surprised if they rely on black box tuning and optimization methods, right? Yeah. That would be weird to me because you want to trust them in one way or another. I think it's also, so I imagine that at some point we understand these systems better, or we understand what the AI is doing and we turn them into hard-coded or heuristic algorithms. But until that point, I think we need all the hands we can get, and AI is extremely helpful in this. It's no longer feasible as a human in the experiments or in the lab to tune 60 knobs at the same time, right? And they all influence each other. And figuring out what the right settings are is I think we really do need AI for this. But I do think, and I do hope that at some point we can ask that AI, or it becomes clear, we can interpret it and understand why it's doing these things. And then we say, okay, so actually it means that this is the right heuristic, we should do that, right? And then the AI can be used for other things. Yeah.
Can we meaningfully claim quantum advantage if verification itself becomes opaque?
Yes, if we can check the answers, right? So for some of the, hard problems, it's hard to compute the answer, but once you have the answer, you can verify. You can just stick in the answer and see if it's correct, right? So if you give me this quantum computer and I ask it, solve this problem, and it gives me an answer, and I can verify that the answer is correct, then I think you have a black box, if you will, or a quantum computer that gives you an advantage, right? If that computer does it faster, better, memory, or more efficient than the classical one. But you can also, so the verification of quantum devices is a huge research field, right? You can use other quantum devices to verify quantum devices, quantum verification. I am not the expert in this direction, but I do know some of my colleagues are, and I know that there's a lot of smart people thinking about how to do verification of quantum devices. And so I'm not worried about this. I think, yes, there are ways to claim quantum advantage if the verification of the answer becomes difficult. and using other quantum devices.
A last question on the machine learning use cases.
Yeah.
Do you see a future where machine learning plays a similar role to error correction, not fixing errors, but detecting regimes of failure?
Yeah. So so if we have those heuristics or those better hard-coded algorithms for fixing the errors, that's what we were just discussing. And then you have a higher level of like the meta level, right? And just maintaining, operating the quantum hardware, things that also the humans would be doing now. And so I see a role for this, right? Also scheduling of the jobs and routing, turning the circuits into useful, mapping them onto the quantum hardware. I think there are definitely places where AIs and machine learning can help operate quantum computers.
Who do you see, Evert, as the game changers in the quantum technology? If they received X amount of money, they would really unlock the main obstacles.
What I would want to, I've never done this, but what I would want to understand is why did transistors win the race? Classical, right? They're also based on quantum effects, but we have different modalities in quantum hardware. You mentioned some of them, the ions and the spin qubits, and we have the photons or the Majorana ones, the topological ones. It's so hard to make a choice and to predict which one will be the right one. So I think the question you're asking on the hardware side is this question, is which of those modalities should we pick? We should just say we are going to focus on spin qubits. They're not the easiest to work with, but we have the whole silicon industry, right? That will solve many of the problems that come after, right? Or we say, let's go for photons because they can work at higher temperatures. They don't have the noise issues because they don't interact, but it's extremely hard to make two photons do something and talk to each other. So all of them have their particular engineering challenges. I'm sure you're well aware of that.
But are there specific persons that you feel that from the area where you look at, that you say, if those people got capital, I believe they can solve an important problem in the ecosystem that will bring quantum forward? Who would that be?
Well, I think of the people I can judge best in these directions are, of course, the people in the field and my colleagues. So, for example, my colleague here, Evert van Nieuwenburg, he is really an expert on all things quantum machine learning and proving which problems can meaningfully be done on quantum computers. I think I would talk to him often, and I'm continuously surprised by his depth of knowledge on these things. I think if he decided, let's make a company on these things, if he wanted to do the DeepMind company with me, then I think that should be.
Okay, that's interesting. Can you give a 2-minute pitch to wrap it up, where you explain the gamification of quantum technology?
Yeah.
Why should investors and policymakers, why should they care?
Yeah, well, I think the most important thing is they should care because it's one of the things that gives you much more immediate value. We've been saying, quantum computing and fault tolerance is decades away, but the bottleneck is not just the qubits, I think, like making more of them and making them more stable. It's also the workforce, especially the workforce. I think people mentioned this, I mentioned this before. It's one of the bottlenecks that limits growth. And I don't want to wait for perfect hardware. I don't want perfect qubits. I want perfectly managed noisy qubits. And I think we can only get value out of them by turning it into this strategic playground, this gamified route where people without quantum background, but the hackers and the tinkerers and the creatives who come up with cool and crazy new ideas that make me go, like I said, like, hey, I didn't know this was possible. This is cool, right? I want to enable those people, right? And I think if I enable those people, we will get value out of finding unexpected new algorithms that can run and that can do useful things with noisy qubits. So that not only helps, giving them those native tools and going to the big AAA studios and have them incorporate something quantum, either in their narrative where I can guide them, or in generating textures that have a different feel than the classical ones, or in random numbers. but it also helps build intuition for broader public, broader audiences with games, which helps building the workforce. And we should invest in them now, even in the younger generations, getting them excited for quantum technology. We will need quantum programmers, and we have to start giving them this intuition early, because you don't find it in real world quantum intuition, unlike gravity. The games are benchmarks. No, I didn't even mention this, but no current hardware provider can run tic-tac-toe real time, right? It's a super simple game, but no one can do that. And now imagine that IBM says, hey, we can run one round of tic-tac-toe coherently, right? And then IQM says, we can actually run 3 of them, right? Then you get this sort of a race that helps drive the hardware. And the final pillar I want to mention is that it's excellent. This is, for my background, for research, right? This is the DeepMind approach, where you say games are the structure that we need to understand quantum problems, how to turn them into structured problems that AIs can solve. And this is a thing that researchers will have to do. This is where we need capital for building such a research institute. You mentioned sovereignty for policymakers, right? If they get intuition for quantum, that really helps them, and which you can also do with games. 40% of people globally play games, right? And doing, Candy Crush on your phone counts. I once had people say, I'm not a gamer, I just play on my Switch, right? But okay, then then you play games, right? And so investors, I would say, if you look at the companies now, I think they are burning a lot of cash trying, keeping up or waiting for this logical qubit to happen. And I don't want to wait for that, right? I want to bridge that gap with, training the workforce and having other people, enabling them making games, making IP for these creative ideas that come out of those playful explorations, and moving quantum from the lab, which it's now, into the living room, right? Where people can play with it and do that, and have my physical tic-tac-toe board, the wooden one I made, on their coffee table, and grow the quantum economy in this way.
Evert, I think it's really fascinating, the gaming initiative. But if you want to start a company out of it, how would you scale it?
Excellent point. I think that we need to then find a way to go viral with this. I'm already getting requests from different points, from the municipality and policymakers, who say, hey, these games are interesting for us because we are not quantum experts, but they lower the barrier. We can get into this, and requests for podcasts, etc. Imagine esports, right? We have already, this year now in May will be the third national tournament of tic-tac-toe, right? We will maybe do checkers, quantum checkers also. And there's more games that are in the pipeline. But now, we do this in the quantum community and people who know about it and are interested about it. But from this experience, especially with a game like tic-tac-toe that we all know, and now I breathe new life into that, if we can find, we make the next quantum Roblox or quantum Fortnite, and we turn this into an esports, right? It's a whole new world and different type of games that I'm sure people will find interesting to explore, to see what it can bring. And so here, I think, that would be the approach, going for making these games a larger global phenomenon, esports, facilitating quantum game tournaments, also of quantum games that other people make. I can see that happening. Yeah.
That would be amazing. And if that happens, I will definitely want to visit and track and watch that. So I hope in 5 years' time that there is the first quantum esport tournament.
And I will share with you the recordings, and if you have time in May for the third one, this is fun. We have exactly this setting where I don't play, of course, because I made the game, but we do the narrating, and we set it up like the esports people, right? With commenting on the moves that they're making and interesting moves they make. So